Thank you. Can you hear me? Brilliant. So yeah, I'm Chris Snow from Vast Data. I've been asked to come here today and basically show you some of the experiences that we've got from the enterprise world in terms of making data findable and usable within large organizations. And specifically what we're looking at doing is trying to see how we can automate research data curation using multi-agents, multi-AI agents. I've got my laptop here and my clicker, so I've got to remember to do two at once. Okay. So, about me, I've been about 25 years in IT. Last 10 years, I've been focused on probably what you'd call applied AI. So I've been helping organizations build models, deploy models, and basically use them to, to help kind of automate some aspect of the business. What we're going to look at today is the research data crisis. So hopefully I'm going to see some kind of, or maybe not hopefully, but I'm going to see some nodding heads here. So HPC centers generate lots of data. Many cases, this data is undiscoverable and it's not FAIR compliant. And as a result of this, PhD students spend months on data engineering, finding the data assets they need to be able to, just to move their research forward. And what I'm proposing here is that with AI agents and also, looking at the vast data platform, how we can automate this process of making this data available. What I've done here is I've specifically tied the research data crisis back to Dirac's priorities. So, coming back to the previous slide, we're looking at things like, we do have a data crisis. How can we curate data? How can we prevent metadata being this bottleneck? And ultimately, I'm hoping what I'm showing you here today shows you that we've got a solution that you can start putting in play to help with some of these issues. So what is FAIR? So FAIR basically stands for findable, accessible, interoperable, and reusable. What we're going to look at today is some of these concepts. We're not going to look at all of them, but we could have future sessions where we kind of layer all of these things together. So what I'm talking about today is a foundation for FAIR compliance. Before I jump into all of the kind of demo and the workflow side of things, I just want to set some terminology. Otherwise, you're going to get lost in the flow. I'm going to start with DACE. So VAST has introduced an architecture called DACE. This is basically completely different from what was available before. So before there was a shared nothing architecture that was released by Google originally. So we've kind of turned this upside down. And what we're having is if you can see in the you can see in this diagram here where you've got data nodes along the bottom, you've got compute nodes along the top in this diagram, and basically everything, all compute nodes can access all data nodes. And what this means is that we eliminate east-west traffic, and it gives us a bunch of properties like we can see on the left-hand side. So linear scalability, we use all flash. We've got some clever algorithms in terms of how we store data so that we can deduplicate. We have an algorithm called similarity, so we can reduce your data storage as it's getting stored. We're decoupling compute and storage, and this gives us really the foundation for what I'm going to show in the next slide, which is VAST's AI operating system, where we've got all the data services you need for building things like AI agents, but being able to do this on kind of massive data sets that you typically see in this space. So what is the VAST data platform? So it's basically a number of different components and technologies. We've got, make sure this builds out. Yep. So we've got the data store on the left-hand side. This is effectively unstructured storage. So you can access the data store using things like S3, NFS, object store. It's multi-protocol, so you can write in NFS, for example, and then read the same data with S3. Where we see this kind of beneficial is things like model training. If we've got data coming in through kind of cloud type APIs, sort of IoT data, for example, that tends to come in through S3, but model training tends to happen on NFS. So being able to have that multi-protocol is a big benefit for us. We then have a bunch of other services around this as well. So we have a database, a very scalable, structured database. Lots of my customers are using this as a system of record where, because of the DACE architecture, we can actually stream in data. It's very, very effective as a streaming transactional database, but also for analytics as well. So if you've heard of HTAP in the database world, this is basically a HTAP database. In terms of it being really good at streaming, what we've also introduced on the platform, and you'll see why later, is a Kafka API. So we've written a Kafka API as a very efficient, lightweight C++ API, but that streams directly into the database. So this kind of gives you some idea of how good it is at streaming type workloads. We've also built a vector database API on top of it as well. And myself and colleagues were constantly talking to enterprises about disruptive use cases. So you imagine kind of in this AI era where we've got huge data sets, trying to get intelligence from those data sets. Lots of organizations are turning to vector DBs and, at a massive scale. So we're talking, hundreds of trillions of records per vector table, and, potentially petabytes as well per table. So very unique kind of use cases. We've also got the data engine. So this is more around, okay, you've got your data structured or unstructured. How do we bring compute to this? So we have a number of engines. I've just got Spark listed here, but we also have things like Trino. So both are open source, well-known kind of analytics engines. We've also got Kubernetes coming as well to the platform. So you'll be able to bring Kubernetes workloads as well. And then on the right-hand side, we're going to talk a little bit about Insight Engine. And what this is basically a kind of chatbot type set of processes built on NVIDIA inference microservices to help organizations deploy query type interfaces across their documents and data. And then on the top, we've got SaaS services. So these are higher level services. So we've got things like cybersecurity. I talked about document RAG. We've got lots of use cases around visual search and summarization. And in many cases, we're talking to organizations, but this is at the country level. So you can imagine, tens, hundreds of thousands of video cameras all streaming their data into vast data, but then that information being available to do something with in real time. So hopefully that's given you some terminology that will make sense now as we look through some of these other slides. So what I'm going to look at is how do we generate data or metadata in near real time. Okay, so I've given an example solution architecture here where on the left-hand side, we have an S3 data folder as an example. So all of this would be hosted on VAST. And what we have is whenever data arrives in that folder, that we can configure it to send an S3 notification. So you can see there we've got S3 event notifications. We then have VAST functions and triggers. So a trigger will listen for the notification and then call a function to be able to process that notification. In this case, we've got some multi-agent curation services. So I've got some examples of these. And then on the right-hand side, you can see that we're writing to the VAST database. So this is basically storing process information. So, what documents have we seen, what we processed, what time did they arrive, and so on. And also on the bottom right, we actually create the metadata JSON. I'll show you an example of what this looks like in the next slide. That example metadata feeds back into the S3 folder. And from there, we've got another set of S3 notifications that then follow the bottom route where we can ingest that data into our document RAG environment. And I'm going to show you kind of this end-to-end flow and what this can give you. So these are some of the agents. I'm not going to walk through all of them now, but these are just an example. We'd probably develop more and different ones depending on your exact needs. But if we talk about the first one, we've got a boundary agent. So if data arrives in a folder, we need some sort of mechanism for determining, is this a root level folder? Is it a subfolder with data sets? And this agent can use, it can use hard-coded logic, but also LLMs, depending on what those requirements are to determine what that folder represents. And then things like data enrichment agents. And in this case, we can have an agent that can inspect files like HDF5, NetCDF, call LLMs, again, to extract metadata and find out what those files represent. And so on. I'm not going to, like I say, I'm not going to go through all of these today. I do have some examples on GitHub. So if anyone wants to, collaborate around this, I can, share the agents that I've created, and we can work together on those. Okay, so this shows just another view of what I talked about earlier. So this is kind of more of a process flow. So so data coming into S3. That then goes to the vast Kafka topic. We've got the trigger, which is listening for events around files being created, updated, or deleted. We then have a function that's the orchestrator that manages the AI agent pool. The AI agent pool then creates this metadata, which we'll see later goes into another process to make it searchable. And then in the middle, on the bottom, the 6, we have processing metadata, which is stored in the vast database, again, to track where we are in the process. So you're not going to be able to see this. I think the slides will be shared afterwards, but what this is an example of is a folder metadata file. So I just talked briefly through some of it. In the top, we've got some information around the folder path, when it was generated, what it was generated by. There's an executive summary. There's key findings around things like what the domain, what the data format is, what variables we have in the file. It's then got a data set inventory as well. So for each file in that folder that are related to that folder, we'd also have metadata for those as well. So, this could be pages and pages long, depending on what data you're storing in a particular folder for your research data. Okay, so now what we're going to do is we're going to look at how we can actually process some of this information with vast triggers. Now, I'm doing a pseudo demo here, so these are just screenshots, but it hopefully gives you an example of the flow we're going to follow today. So here I'm logging into the vast pipeline builder. And from here, you can see we've got some triggers, we've got some functions and pipelines. What I'm going to do is click on the left-hand menu, and we can see we've got pipeline management. So I'm going to click on that. So this is a list of pipelines that myself and some colleagues have just been creating as examples. On the top right, we can click on Create New Pipeline. We can give that a name. So I'm going to give it a fair pipeline. We can tell it where this pipeline is going to run on what Kubernetes cluster. So I'm going to create that pipeline. That's taken us back to the list of pipelines. And I can right-click on it and go to Builder. When we go to the Builder, we can see a canvas. And from the canvas, we can drop functions and triggers, or I should say triggers and functions. It's normally in that order. So if I click on New Trigger, I give a trigger name, so I'm calling this a fair data trigger. We've got different types of triggers. This is an element trigger, so basically we can have triggers that, as I said, happen on S3 notifications, and we can define the bucket where those triggers go to, where those documents sit in terms of S3. Next, we're going to create a function. So this is the Python code that calls the agents. And if anybody's created cloud functions, is basically the same kind of technique here. So once we've created that metadata, so the result of that would be a continuous process to create your metadata. It can then go into our insight engine. So normally insight engine from the enterprise has been documents or PDFs or spreadsheets or kind of enterprise type documents. But here we can feed in the folder metadata. That then gets ingested, it gets vectorized, chunked, and stored in the vast vector DB and the vast database. And then it's available through the, all of this is orchestrated through the NVIDIA NIMs, so the NVIDIA Inference Microservices. And on the right-hand side, we can then query that data. This is just a more detailed view, but this is kind of more like a reference architecture for the that type of process. So what I'm going to show you now is a manual kind of way of uploading this data, but normally this would be automated in practice. So here we're going to choose a file. We're going to choose the folder metadata file that we saw earlier. So we can upload that. That's uploaded successfully. That's now going through the process to be vectorized, chunked, and then basically made available for search. So search, now I'm going to represent basically a researcher, for example, in your organization. So you can log into the chat interface. From here, there's a bunch of example queries that you can run. Let's jump back to the document. Again, you can't see this, but there's some information in here saying this is a climate model simulation, CMIP6 experiment. I've just shown you that because I'm going to then take some of that information and put into the query. So find me information, find me data for climate science, CMIP6. What the LLM's done now is it's been able to, it's vectorized my search query, it's gone to the vector database, it's found my metadata, it's given me a summary of that metadata. Towards the bottom of the, underneath the line, it also gives me an answer breakdown. So here it says there's 5 sources. And what that means, if I scroll down a bit further, basically there's 5 chunks. The first chunk is, I think the information's come from the overall metadata. The next chunk of the metadata file is then some of the climate data that was in that folder and so on. So this then gives us a way to kind of locate the data we're interested in. So yeah, sorry, I got out of time in my timing, but never mind. So in conclusion, so I've taken some of the, basically this is what we're seeing with the enterprise. So huge reduction in curation overhead. Oops, I'm going. Yeah, so huge reduction in data curation. Speeding up your research discovery, and hopefully giving your kind of researchers some kind of competitive advantage about finding information quicker and making it more usable. And then, how do you get started? We've got a booth at the back. I've got with some colleagues, so James McClung and myself. We're here both days. Yeah, just come and have a chat, and we can see where we go from there. Brilliant. Thank you.
Thank you, Chris. Any quick questions for Chris? Yes, sir.
Thanks a lot for a very interesting talk. I'll try to make it quick. I'm a scientist, I'm a chemist. So my data sources are machines, are electronic lab books, or even handwritten ones, or all sorts of things, observation in the lab and so on. How do you handle this kind of really heterogeneous data sources compared with CCTV, for example?
Really, really good question. So, I mean, I started off creating some examples, which I put out onto GitHub. I think this is, one of the challenges we need to address. But I think as LLMs evolve and get, stronger, I was really surprised at how much could be extracted in terms of metadata from the files that I took and I was using. But yeah, great question. I think something we need to look at. Thank you.
All right. Thank you, Chris. Now.
Thank you.